In chemistry, resonance is the movement of pi electrons and lone pairs between different atoms. To explain resonance, let's check Lewis structure for carbonate ion, CO3, with 2 negative charges. Lewis structure for carbonate is this. I draw each oxygen with different color. So carbon has a double bond with one of the oxygens, and the other oxygens have a negative charge. Now, double bond can be between carbon and any of these 3 oxygens. So there are 2 other, we can draw 2 other Lewis structures for carbonate. This is the second Lewis structure for carbonate. As you can see, the double bond is between carbon and blue oxygen, and there is a third resonance. There is a third Lewis structure, and in the third form, double bond is between carbon and oxygen on the left side, the green oxygen. We can use arrows to show the electron movements for interconversion of these 3 Lewis structures. For example, in the first form, for interconversion of the first form to the second form, one of the lone pairs of the blue oxygen will form a pi bond between carbon and blue oxygen. And now the pi bond between carbon and red oxygen has to break because carbon cannot have more than 4 bonds. So both oxygens of this red bond will collapse on red oxygen, and we will have the second form. As you can see, these two forms interconvert to each other by movement of lone pairs and pi electrons. And we call these 2 resonance forms, and we use an arrow like this, a double-headed arrow, which means these 2 forms, these 2 structures are resonance forms. For interconversion of the second form and the third form, one lone pair of the green oxygen forms a pi bond between green oxygen and carbon, and pi bond between carbon and blue oxygen will break, and both electrons will collapse on blue oxygen, and we will have the third form. And again, we use this double-headed arrow to show that these forms are resonance forms. Remember that this double-headed arrow that we use to show resonance contributors, resonance forms, is different from the arrows that we use for equilibrium. In equilibrium, both forms A and B actually exist. But when we draw this arrow, the double-headed arrow for resonance, actually none of these forms really exist. And the real structure of carbonate ion is something between a combination of all of these, and we call it resonance hybrid. And I draw it here. So we have the carbon bonded to 3 oxygens, and pi bond and the lone pairs are distributed between the carbon and all of these 3 oxygens. And there is partial negative charge on all 3 oxygens. Okay, so this is resonance hybrid. The real structure of carbonate is this structure. These forms that we draw, the resonance forms are the extreme forms. So they don't really exist, and the real structure again is the resonance hybrid. And we should put the resonance forms in a bracket. Another example for to show resonance is this allylic carbocation. We can draw another Lewis structure for this carbocation, which is this form. Okay, if I label the carbons as A, B, and C, in the first form, pi bond is between A and B, and positive charge is on C. In the second form, in the second Lewis structure, positive charge is on A, and pi bond is between B and C. So these, as you can see again, in these two forms interconvert to each other by movement of pi electrons. So if these pi electrons move over here, we will have the second resonance contributor. And again, we show this double-headed arrow, which means these two structures, these two Lewis structures are resonance forms, and we put them in an arrow. And the resonance hybrid, the real structure of this carbocation is this. So pi electrons are distributed between A, B, and C, all three carbon atoms, and a positive charge is distributed on carbon A and carbon C. Distribution of electrons and charge make this carbocation more stable. In general, distribution of electrons and charge, positive charge or negative charge, make the molecule or ion more stable. And for that reason, resonance makes the molecule or ion more stable. Why? Because in resonance, we have distribution of charge or electrons throughout the molecule. Okay, what is the difference between the pi electrons in this carbocation here and the pi electrons in this molecule? These two electrons, the pi electrons in this carbocation, are not always between A and B. They are not localized on between A and B. And they can move and go and be between B and C in the other resonance contributor. But in this molecule, the pi electrons are always between A and B, and they cannot move anywhere else. So we call these two electrons, these pi electrons, localized, and these two pi electrons in the carbocation are delocalized. To draw resonance contributors, resonance forms, we have to follow few rules. The first one is that we never move the atoms. So we never move atoms, we only move electrons. But what type of electrons? Only pi electrons and lone pairs. When we are drawing the resonance structures, we never break a sigma bond. We never break a single bond. And we also never exceed an octet for elements on the second row. For example, for carbon, nitrogen, oxygen, they should never have more than 8 electrons around them. Okay, so to draw resonance structures, we have to move pi electrons and lone pairs. But how we should move these electrons? Again, there are a few rules that we have to follow. One of them is we move pi electrons or lone pairs toward a positive charge. For example, if we have this carbocation, the first rule tells us move pi bond or lone pair toward a positive charge. So I can move this pi bond toward positive charge. So pi bond breaks and it forms a pi bond between B and C, and positive charge will be on A. So these two are resonance contributors. Now, if I have this carbocation, can I move this pi bond toward positive charge? No. Why? Because there is an sp3 carbon in between. So the positive charge and pi bond or positive charge and lone pair should be on adjacent carbons. You cannot have sp3 carbon in between. That doesn't work. We can also move pi bond toward another pi bond or lone pair toward a pi bond. Example, we have this compound. We can move pi bond toward pi bond. And again, pi bond should be on adjacent carbons. They cannot be you cannot have an sp3 carbon in between. So I move this pi bond here. Now remember, we cannot exceed octet for the second row elements. For example, for carbon, if we break this pi bond and form a pi bond between these two carbons, now this carbon will have 5 bonds. Why 5 bonds? Because there is a hydrogen, an invisible hydrogen here. Okay, remember, in bond line structure, we don't show hydrogens which are bonded to carbon. So when a new pi bond forms between carbon B and C, pi bond between C and D has to break and it will collapse on carbon D. And we use this double-headed arrow for resonance forms. So there will be a negative charge, a lone pair, on D, and a positive charge on A, because now A has only 3 bonds. And of course, there is another resonance contributor, because pi bonds can move to the other direction, like this, okay? And the other resonance contributor would be this form. And the actual structure of this molecule is this, the resonance hybrid. So the pi electrons are distributed all over the molecule, and that makes the molecule more stable. So resonance will cause more stability. Another example is this carbon anion. Okay, we can move pi bond toward lone pair toward pi bond. So I move this lone pair toward pi bond, and this now carbon has 5 bonds, so pi bond has to break on this carbon at the end, and this is the structure of the resonance contributor. Okay, A, B, and C. So pi bond between A and B becomes a negative charge, a lone pair on carbon A, and a new bond forms, and a lone pair on C. This lone pair becomes a pi bond between C and B. Now, can I move this pi bond toward the other pi bond? No. Why? Can I do this? No. Because there is an sp3 carbon between the pi bonds. So we cannot do this. We don't move electrons toward sigma bond or toward the carbon which is sp3.